Swayam Prabha. Digital India. Educated India.
Good day to all of you and welcome back to this class in which we are going to continue our discussion on covers for landfills. Last time we talked about several layers in the cover system. Surface layer, then next protection, next barrier, next gas collection, and then foundation. So many layers and so many interfaces and so many separators and filters in it. But I talked about replacing some of these layers with man-made materials. So what I'm going to do is, let me see whether I'm going to show you some of the materials. So here you will see that in the drainage layer we have a sand and gravel layer, and below that there is written GeoNet, overlying geomembrane, and there's another word called geocomposite. We have all seen a geomembrane last time, right? Now I'm going to do with you GeoNet overlying a geomembrane, and I'm going to do with you geocomposite. So first I'm going to show you these specimens, and then we'll carry on the discussion from here. So let's see, starting with a geomembrane, then a GeoNet, and then a geocomposite. So we all remember this smooth geomembrane. And we also all remember rough geomembrane, and this is going to become very important in covers. Now I'm going to show you, we remember geotextiles, non-woven geotextile, right. Now I'm going to show you a device, a material which looks like this. It looks like a net, right. It has a thickness of few millimeters. And suppose I have a geomembrane, I'm taking a geomembrane and putting this net on top. Can this net replace the sand? That's the question. The water will be percolating down from the surface layer and the protective layer into the drainage layer. It will come and rest on the geomembrane. If I have a net on top, which means there is a finite thickness of air space on top, and if this is sloping downwards, then water can flow along the plane like that, along this. I am bothered about the fact that fines should not come into this. So what will I do to prevent fines? I'll put a separator. So now I have a material, geomembrane at the bottom, a geonet at the top, and a filter geotextile above it. You will learn more about geonets in your course on geosynthetics. But if this can replace the sand, so something which is 5 to 10 millimeter thick is replacing the sand, provided it has the capacity to carry the same amount of water as the sand that we had, right? So we will be dealing with issues of permittivity and transmissivity in this material, but this is one set of options. Now, so that it should not be difficult to install it in the field, we have something called a geocomposite. What does it look like from the top? Is it a geomembrane or a geotextile? Very good. This is a geotextile. It's a non-woven geotextile which looks like a blanket. On both sides, if I see, I have a geotextile, right? But there is something inside it. If I look at it, can I see some black things? So what is inside it? Let me try and peel off a corner and decipher this for you. If I peel off the corner, what do I see? So there's a geonet with a geotextile on top, and if I look at the other side, it's got a geotextile on top. This is bonded to it. So what is the advantage of this? This comes in the form of a roll, a big roll. So you are able to, this is another one, I can show you a thicker one. This is black, carbon black, carbon black. If I peel off one of the corners, you can see a geonet. So this comes in the form of a roll, and it can be laid on top of the geomembrane. I have a geomembrane, and on top of it I have a geocomposite. So this replaces the 1 foot thick, 30 centimeters thick sand layers, and it should have the capacity to drain away the water. And before I move away from here, I also want to show you one more material which looks like this. It is called a geogrid. It's a very strong material. I mean, if I gave it to you with your eyes closed, you would have said, sir, this is some metallic mesh. It's a reinforcing material called a geogrid. This also you will study about it later, but we will introduce it to you in this class. Okay? The difference between a geogrid and geonet is stark. Very small openings which are orthogonal to each other in the geonet. These are at right angles to each other, much larger apertures than in the geonet. Geonet doesn't have much strength. It is not for strength, it is for in-plane flow of water. Whereas geogrid is like a reinforcement, a mesh, a reinforcing mesh. So when I look at the materials here, I'm saying I can have a drainage layer made of sand and gravel, or I can have a drainage layer made of geonet overlying a geomembrane. So on the geomembrane you can put the geonet, on the geonet you can put a geotextile, and on top of it you can put the protective layer. This will be cheaper than a geocomposite, but it will take some time to install it. First you will put the geomembrane, then you will put the geonet, then you will put the geotextile. There are 3 operations. If the geotextile, if the geonet plus the geotextile is available as one unit, it's one roll, so the number of operations in installation go down. So that is a geocomposite. So I can use a geonet overlying a geomembrane for drainage, or I can use a geocomposite. And the same can apply to a gas collection layer. The same can apply to a gas collection layer, because gas will flow at a faster rate in a geocomposite than water. We are worried about erodibility of the topsoil. So as we said, gravel is low in erodibility and coarse sand is low in erodibility. Soils which have high silt content and fine sand content, they are the ones which erode the maximum. Will clays erode more than silts or less than silts? Because the clays are finer particles. The finer the particle, the more the erosion. Because of cohesion, clays have net negatively charged particles, they remain plastic in nature, they have a cohesion. So as the clay content increases, the erodibility decreases. Also it is observed that when you have organic content in the soil, it supports vegetation and therefore it decreases erodibility. So the best materials for low erodibility are gravel and coarse sand, followed by clays with high organic content. Then silts and fine sands have a erodibility problem. If you grow vegetation on silts, that's fine, they are not going to erode. But before you are able to establish the vegetation, remember, you are going to have a landfill on which you are going to put all these soils. In how much time do you think that you can grow grass on soil? A day? An hour? A week? A month? I would like to see the magical grass. It's been said that you can grow grass in 10 to 15 days. I can transplant the grass from one location to another, but for a proper grassy cover to get formed, it will take a month or more. Or you have to get these cut pieces of ready-made grass, which are much more expensive, to be placed on the soil. So the issue is that till the time the vegetative cover gets established, you are faced with erodibility problems. So before the monsoons, please have your vegetative cover in position. So some of the cover design aspects which we are going to deal with are the components and their specifications, the thickness of the components. We've done this. The separators, protectors and filters, we've looked at them. We're going to look at stability of slopes. We are going to look at erosion control. We are going to look at surface water drainage, gas collection systems, and the influence of settlement and subsidence on the materials that we use. First, remember that how much water is percolating into the waste is precipitation minus the surface runoff minus the soil moisture which is stored inside the soil. We have to remember that the topsoil and the protective layer is not totally saturated, and if it is not saturated it will store some extra water. Beyond the field capacity it will come down. And evapotranspiration is also something which makes the water go back, because now you are having vegetative growth at the top. And then finally lateral drainage. So after all this is removed, do you get percolation below the barrier there? So if precipitation is P, then typically the runoff depends on the type of soil, the vegetation, the slope, but runoff will be high when soil is fine grained, vegetation is well established and slope is high. But if precipitation is falling on gravel, what will happen? It's coarse grained, vegetation cannot grow on gravel, the water will go in. So depending on the soil, you will have infiltration which may be 90% to 30% of the precipitation. For paved area, as I said, all the water runs off. And infiltrating water is lost through evapotranspiration and partly stored in the surface layer and the protective layer. Balanced percolation is drained laterally. Leakage through the barrier enters the waste. And typically, to enhance surface runoff, we are giving at the top a slope of 3 to 5% to enhance the surface runoff and lateral drainage. So remember, all your covers are convex. All your covers are convex. There are no covers which are horizontal. 3 and 5% are significant slopes on the covers. So if I look at it, when my water enters into the drainage layer which is above the geomembrane or above the barrier, where does it go? It goes down the slope and it goes into a drainage pipe. Is this leachate? So it's like surface runoff. So please understand, rain is falling on this surface, right? This water which is falling on the surface will also run off. It will go to the storm water drain here. This water will also come to a drainage system which will be connected to the storm water drain. Only the water which goes into the waste becomes leachate and goes down. So you can have several arrangements. You can have an arrangement like this, which is the same thing here, or you can have a trench made of cobbles and the water can be taken out in the storm water drainage system. So this is important. In some of the landfills, this detailing is not done properly. You know what happens? This becomes connected with this. This is a very small distance. If you leave this somewhere here, it will sort of reverse flow into this. This connection is very important. You should have no chance of the water which is coming from here going into the landfill. This junction is very important. We'll do it later. which landfill is more affected by surface water, above ground or side slope landfill? The problem is the moment you have side slope landfill, the water is coming down the slope, it will tend to accumulate. So as I said, you have a 3 to 5% slope here and 3 to 5% slope here. This slope which I am talking is at the top of the cover. It's not the side slope. The side slopes have a different value which we will talk about. So please see the arrangement. You will have a diversion channel or an interceptor channel which should not allow the water to come onto the landfill. Whatever falls on top of this should go out from a drain here and a drain here and a drain at the berm, and should go to the storm water drain at the toe. And a better view, allow the water to run off, down, have a berm, down, have a berm, down, have a berm. On the berm, have a drain to collect the water. If there is no berm, the slope may be stable, but once it is more than 8 meters in height, the water velocity becomes very high. So long slopes without berms, what happens? The erosion starts because the velocity of the water is high. These berms act as energy dissipators. The water comes down and is collected. So it's good to have a berm, and the berm is 3 meters wide because you have a road on it as well, your inspection road, and the drain is only at one side of the inspection road. So very important detailing for a landfill. If you can collect most of the surface water, all your problems are solved. If the surface water cannot run off the landfill top, it's going to go inside. It's going to go nowhere else and inside. So we should take care of the surface water very carefully. If I look at the top of a landfill from an aircraft or a drone, let us say this is the top of a landfill. So what will you find? 3 to 5% slope, 3 to 5% slope, 3 to 5% slope, 3 to 5% slope. Then have a drain here. This captures all the water which is falling on the top. These are the two berms. Okay? So there is a drain here on the berm. So whatever is captured in this drain has to be connected to this drain down the slope. And whatever rain falls between these two drains also is connected in this drain. Then it goes to the next berm, and finally it reaches the toe drain. And this is all surface water runoff, so it can go into the storm water drainage system of your landfill. Very, very important. You have a convex top, but you're collecting it. If I give you an engineering drawing of a landfill, have a look at this. This is the way the land was available, and this is the landfill area. And you can see a lot of contours, right? But you can see on this, it has got every area from which the water will be connected, where is it flowing, where are the drains, what are the cross connectivities, and eventually they will reach a toe drain at the bottom. So I can't, the details don't stand out, but remember all these are drains which are collecting the water and sending them to a toe drain, which eventually gets connected to the drain, stormwater runoff drain here. And this is the concept of the diversion channel or the interceptor drain. If you are on a side slope landfill, please catch the water and divert it from the sides. Don't let it enter the landfill. The other thing we talked about was the gas collection layer, right? And please understand two concepts, the concept of venting and the concept of gas collection for energy recovery. Venting means you are still allowing the gas to go into the atmosphere. But venting means that the gas goes to the atmosphere in specified vents. Suppose today you have developed a landfill, you don't have the money to collect the gas and convert it into energy, you don't have the investment. You put in vents so that tomorrow you can attach a pipe to these vents and collect the gas. So one can be a cover with no vents, in which case the gas will pass through the desiccation cracks and the high permeability zone and go to the atmosphere. The other is you have the gas collection layer. So the gas collects in the collection layer. and the pipes has holes in it, perforated pipe, and it goes up a vent, which basically is nothing but like an inverted U, doesn't allow the rainwater to come in and comes out from these vents. And if you are using a geomembrane, then please note that a connection between the geomembrane and the vent is very important. Otherwise, water will start going from the side of this rigid element. When you put a pipe in soil, after some time you'll find there's a little bit of separation depending on whether it's summer. The water will try to go in and create more leachate. So you have to put the geomembrane around it to clamp it properly. So when I want to recover gas for energy, please understand you will have this gas collection layer at the top, but you will also have deep gas collection wells, which are not shown here. So this, I'm not trying to show you gas collection for energy recovery. I'm trying to show you if you make a normal landfill on a municipal solid waste dump, and even if you are not using a geomembrane on the top, please put the vent pipes, because you will put a gas collection layer. It is mandatory. Once you have put the gas collection layer, you should be able to collect the gas through the vents in the future if you want. You see, today there are no restrictions on greenhouse gas emissions. Tomorrow there may be a international law which will say that all landfill gas will be captured and burned, flared, so that methane gets converted to carbon dioxide. So we need to have these vents in all locations. I talked about the importance of cover slopes. Cover slopes are going to remain exposed for 50 to 100 years. The operator always wants to make very steep slopes so that he can store more waste. We would love to have vertical slopes. But we need to look at the slopes. We have this slope, the cover slope, we have the liner slope in excavation, and we have a waste slope. So typically when you excavate soil, you will find that slopes of 1.5 to 2.5 horizontal is to vertical. Please note, I think this is not written here. This horizontal is to vertical. So these are flat. 1:1 is 45 degrees. These are flatter than 45 degrees. These are usually used in soils. We also use similar slopes for the temporary waste dump. This slope is created because I am filling the waste like this. So I have a temporary slope. So this is also kept at 2:1, 1:1. But along the liner and along the cover, the slopes are even more gentle. If you look at the cover, we are talking of slopes of 3.5, 5:1, very flat slopes. So you wonder, what are these geotechnical engineers doing that they can't make this 1:1? Traditional slopes which you have in soils, 1.5:1. And also along the liners, the problem is you have put a geomembrane. The moment you put a geomembrane, it's a slippery surface. Two things happen. Water will get stuck at the geomembrane and start to travel along the geomembrane. So I think we need to understand this. Suppose this is the slope, this is my compacted clay barrier, and this is my geomembrane. Whether it's in the cover or in the liner, it's the same. So I said smooth geomembranes are troublesome because the angle of shearing resistance is low. Let's make it rough. So I can make this rough. So now my angle of shearing resistance is not low. However, what is happening? I have a drainage layer on top. Water is coming down, leakage water or leachate or surface water. At the top, if you see surface water coming through the protective layer. Normally, if the geomembrane was not there, it would go and hit the soil. It would be first make the soil more wet, and then it will go down. So this was the original travel. In soil, water always travels down. But what happens is you hit geomembrane. It is like hitting rock. So what happens in hilly regions? Rainfall is on the slope, water goes down. Where it hits rocks, what happens? It starts to flow along. When it starts to flow along, at the moment the seepage forces are downwards. But the moment it starts to flow like this, the seepage forces are downslope. It is destabilizing the whole. And therefore, that is the cause of instability. So two causes of instability. One, too many interfaces. Two, flow occurring along the slope downwards. And this causes the slopes to be flat. In the liner, it doesn't matter. Your excavation is going to be there for a year at max 2. Right? Then the waste would have reached the top. The waste would have been filled. So the slope no longer is unstable because there is a stabilizing waste here. But what happens in the cover? In the cover, that is going to be there for years. And remember, just think of Bombay rain or wherever you come from. If you have very heavy rain, imagine it's taking place for 8 hours. It's falling on the slope. Bulk of the water is rushing off from the top, right? Because you have very good vegetation. For 8 hours, the water is rushing off the top and it's going into the soil, and then it is rushing along the so water is rushing on the top downwards, water is running inside downwards. What do you think is going to happen to the soil if you don't design it properly? It will definitely tend to move downwards unless you have designed it for slope stability. So therefore, the gentle slopes. Can we make them stable? Of course we can make. We can make anything stable. We can make a vertical slope and put a concrete wall. Engineering solutions can be for everything. But the issue is, would the concrete wall then serve as a liner or a cover or what? And will it be able to take the settlements of the waste behind it? You put a wall and the waste settles, what's going to happen to the wall? So remember, slopes of along the geocomposites, not the geocomposites, sorry, along the composite liner systems are very gentle. We can make them steeper. There's a separate discussion on slope stability. So instability occurs because of slope inclination, low interface shearing resistance. No matter how rough I make my geomembrane, it still is not having the highest phi dash. Large thickness of the soil on top. Vehicles will travel on this cover while you're making it. Seepage forces during rains, earthquake forces will occur, and others. So all these interfaces, it's not just about the interface between the geomembrane and the soil. Suppose you have replaced the compacted clay liner with a GCL. We talked about a geosynthetic clay liner last time. What's inside the GCL? Bentonite. When the bentonite is hydrated, it is like swelling soil, fully saturated. Very low angle of shearing resistance. So even this has a problem. So all these interfaces, in fact, bentonite manufacturers will tell you that if you are going to make a slope steeper than 3:1, you have to use a special bentonite which has got a special GCL which has got a reinforcement inside, which does not allow failures to occur. We'll look at this in detail, but I'm just showing you some examples. It's the same cover, topsoil, drainage, geomembrane, compacted clay liner. First we used to use smooth geomembranes. I made it a little thorny so that you can get, now we are using textured. The question was, first we only started doing texturing at the top, making it rough at the top so that there was a good phi dash with the sand. But then now they are texturing at the bottom as well, so that there are good roughness with the clay as well. Now, how do these cover options change? Because now I told you about geocomposites, geogrid. Here, if the soil is too steep and this soil is slipping down, I can put a geogrid. I showed you a geogrid, a reinforcement. I can put a mesh inside the soil and hold it on the top by anchoring it in a trench. So soil wants to go down, factor of safety is below acceptable, the geogrid is holding the soil. This you will study about more in geosynthetics. I have a big problem. The sand is 1 foot thick. It's too heavy. And W cos alpha, you remember the downward force is pretty high. You've done slope stability, you're doing slope stability. Look at it as slope stability of infinite slopes. I want to reduce the thickness of the sand. What do? I go and buy a geocomposite. A geocomposite is only, what, 10 millimeters thick? We just showed you one. Lightweight. So the W is decreasing, therefore the downward force is decreasing. So here you have a geomembrane which is textured with a geocomposite and the other layers on top. Even better, you don't want to use compacted clay at the bottom, you're not getting clay. Let's use the GCL. I'm not a strong proponent of GCL. Whenever you want to use GCL, you need to put a thick, low permeability soil beneath it. But these are options which you can also consider. Finally, you may put a geogrid, a geomembrane with a geocomposite and a geogrid. Sorry, I call this a geogrid. This is a geogrid which will prevent the sand from sliding off, but I can reduce this and put a geocomposite instead of it and put a geogrid. This holds the whole soil together. So a large number of alternatives, as you can see, with natural materials and man-made materials. Currently, in the developed world, a lot of geosynthetics are being used. In India, we are still dealing a lot with natural materials. But gradually, these are also coming into play. But be careful. Always design a system which will last for a long period of time and not be affected by too much tears and punctures at the time of installation. So this is a very nice final cover system of one of the landfills. You can see grass, you can see berms as I talk to you. You also have drains and you can see some vents. This of course is the temporary cover system. Before the monsoons come, you've got waste here, so it's stockpiled in a temporary cover system. This is yet another landfill, grassy slope. You can see this drain. This is the stormwater drain. Stormwater drain at the toe. These are the berms which have drains in it. 1, 2. Those berms allow the water to flow through this, and this is all segmented, prefabricated units. Why? Because the surface may settle. So you allow the water, it comes out to this and is carried away. This is the laying of a cover system. Geotextile, geomembrane, soil. This is finally trying to make vegetation grow before the monsoons come. So you are grading the soil and you've got grass. You can see the kind of soil they are using. They are using local soil, but it's got some gravel content. Can you see that? And eventually, of course, this is what it looked like. But the story is that this can also happen. This is the drain which carries the water downwards. This is the erosion which has taken place. When you make these layers very thin, then the geomembrane can get exposed because you can slide along this. So unless you have a good vegetative cover which is formed and sustained, if you make the things very thin, they are highly prone to erosion. If it was thicker, then at least you would have an erosion gully, but you would not have reached the level of your geomembrane. This is also another shot which I might have showed you. This was temporary coverage before the monsoons. And this is a big contract. They call a regular contractor who puts all this thin geomembrane, then he puts bamboo, then he puts these sandbags, because when you have gusts of wind, it blows. And this is a hazardous waste landfill. So the more leachate you make that gets produced, the more money you have to pay to the ETP, and the owner wants to make profit. This is the situation. That's the final cover system with the soil on top, and that's the green vegetative cover. Vent. Very expensive to maintain this. Looks very beautiful, but very expensive to maintain this. You need to water it. If you don't have water, you have to buy the water. So this is the green landfill, grassy green. This is made of rubble masonry. But the Pollution Control Board is saying this is not green. And two issues here. If this settles with time, there are going to be a large number of cracks. You can repair it, no doubt about it. But this is hazardous waste landfill. It's not settling that much. You can't use this on a municipal solid waste. There are huge depressions on municipal solid waste landfills with time. and then they are trying to make this green. I'm standing here looking at the green, I'm standing on the green looking at the rubble masonry. And in rubble masonry, now they are growing jatropha to make it look green. But children can come and play here. Of course, I'm not saying that children should come on hazardous waste landfills, but you can have limited public use if you have a very intense monitoring system. No gases or liquids are emitting out of it. But you can't come and play on the rubble masonry. And here are more efforts to make the rubble masonry green, grow some plants and creepers. This is for the green look. This is at the Ghazipur landfill. On the slope they were using paver blocks because soil was not stable. We'll look at it under slope stability issue, but I just want to show you that's grass in the paver blocks along the sides. These are geocells. I said geocells filled with soil. Geocells are nothing but 6-inch high accordion arranged bands of geosynthetics. You can fill soil in it and hold it. Put a geogrid. You can see geogrids at the bottom, and that's the geocells. That's the rock toe, and that is the finished slope. And these are the drains which are taking the water down. These are paver blocks. These are geocells with soil. So one of the things which bothers us is about settlements, right? And what bothers us really is if you have uniform settlement, I talk about 10%. If I'm saying we are having a convex top, if the settlement is uniform, it doesn't bother us. But the issue is if you have a local depression, right? If you have a local depression, this is going to pond up with water. And please remember, once you have a local depression, you have a tension crack at the bottom, right? If it is flexible, the tension crack will not form, but how flexible can you be? So one of the indicators is in highly biodegradable wastes, how much tensile strains can talk of. So we say soil is flexible. We said soil is flexible. It can take tensile strain of about 1%. Okay. HDPE, I told you last time, elongation at break was how much, or elongation at yield? Did I give you some values in the liner system? Yes, I did. 50% to 100% is what we were talking about. But that is when you pull it in one direction. You'll get 100% means that it is elongated to double its length. But this is axisymmetric in both directions, because when a depression is formed, tension is in this direction also and in this direction also. So then the extensibility is 20%. If you are expecting more, you can use LLDPE and PVC. Why is HDPE used in the liners? Is because it is most resistant to chemicals. LLDPE and PVC and PET are not that resistant to chemicals. There are some chemicals which will affect them. So HDPE in the liners, but if you are going to have large craters forming on your landfill, then these are having 80%. And geosynthetic clay liner manufacturers claim that they are better than soils. This is 1%, they can take 7 to 15% strains, right? So if I can have 1% strain, then the maximum distortion that I can have is 0.15. After that, soil will not work. If I have 20% strain, then the maximum distortion that I can have is 0.6. It's simple geometry. Allowable differential settlement is the allowed deformation into the radius of the depression. So let us say you are expecting a depression to form here. Okay. What radius would you like to choose? Local depression. This is not the whole cover settling. Whole cover may be 100, 200, 500 meters wide. But a local depression may be 10 meters wide. Right? A 10 meter wide. So radius is 5 meters. Or let's say 20 meter wide depression. Huge one. Radius is 10 meters. If you have 10 meters, what is the distortion which is allowed for clay? 0.15 into 10 is 1.5 meters. So as long as the cover is settling by 1.5 meters, clay will not have a tensile crack. But if it goes beyond that, it will. But 20% is what is allowed in 20% is what is allowed in geomembrane HDPE. So 6 meters deep it can take. So therefore, for tackling settlements, you need to have either repair taking place. See, it's not an issue. If you are repairing it very fast, which is what I'm going to show you next, then this depression will not form if you are having a weekly inspection. So how do we do cover repair? If a depression is formed, you've got the problem is if it's formed, you can have ponding and you can have problems. So you come back and dig this up. You cut this geomembrane, fill up here the soil at the bottom, and put another piece of geomembrane on top. You bring it back to its convexity. So how often you are repairing makes this depression smaller and smaller. If you see it early, you can repair it. So this is the way to repair covers. So covers will undergo large settlements. Long-term settlements can be of the order of 50 to 30% of landfill height. Short-term movements of half to 1 meter. So whenever you have a depression which is local, see when I talk about 15, I'm talking about the whole thing settling with time. But local depressions which form are typically half to 1 meter. And these can cause pondage, so regular repair is required. So soil can handle 0.5 to 1 meter, but soil will not handle much larger depressions. Now I'd like to conclude by talking of, we've been talking of dry tomb landfills, we've been talking of putting elements which don't allow water to go in. But you will come across two terms which are used very often: evapotranspirative covers and capillary barriers. You will have covers which are different from the ones we are talking of, which are not yet used in the country but are used in arid and semi-arid climates. An evapotranspirative cover is one, you have soil. Let us say I'm going to have 100 mm of rain, right? So if I can make the soil, design the soil such that this 100 mm of rain never goes through it. It falls, it runs off, whatever comes inside is held as storage, and then the plants give it back up. You don't let the water reach the bottom. So in arid and semi-arid climates, this all works on capillary action. You have to use fine-grained soils because they are able to hold more water. Typically use gravel, always go through. Use sand, all will go through. So silts and clays and silty clays and silts. So you can design relatively thick covers in which water can be held and evaporated. So this is the new concept which is coming up. It requires very strict quality control. And we looked at a calculation for Delhi, and we need pretty thick evapotranspirative covers. But what their philosophy is that they are doing away with a geomembrane or a compacted clay barrier, and they are saying we will put covers which will not allow the water to go through. But you must have some acceptable limit of water which has to be allowed through. So evapotranspirative covers and capillary barriers are systems which don't allow the water to go below the cover purely by the holding capacity, the capillary action, and having plants which will send it back up. So in arid and semi-arid climates, evapotranspiration will normally be more than the precipitation which takes place over the year. But at peak time, precipitation will be more than the evapotranspiration. At that time, the soil should be able to hold it, and your plants should be able to take out that water from the system. So with this, we come to an end of our discussion on covers. You would have now got a fairly good idea of what the covers and liners look like, as well as the alternate materials which we use. One of the questions which one would like to reflect upon is, if we are talking of geocomposite liners at the top, geocomposite drainage systems at the top in the cover, can we also have geocomposites for drainage in the liner system, because on the liner system also there is a gravel and sand drainage layer, leachate collection layer. If I can have water coming from rain into the top of the cover and replace the sand with a geocomposite which allows in-plane flow of water, can I use it in the leachate collection layer? And the answer is no, because geocomposites can become clogged by the leachate which comes down, not by particulate matter, but by the organic growth of various kinds of organisms in the leachate. Whereas the sand and gravel systems are 1 foot thick. So they have pipes in it with which you can backflush the systems. So geocomposites are not considered for leachate collection layers at the bottom, but they are considered for the drainage layers and the gas collection layers at the top. So any questions that you might have? Something which bothers you, or you have a better thought about how we can do these covers? So many layers, something by which we can reduce. Anyways, think about it and we'll discuss it in the next class. Okay.